So in Chapter 7, we had kinematics. And those are those problems where we deal with, I give you the acceleration or the velocity or the displacement, and you need to figure out what are some of the other quantities. So largely using these two equations. And I think probably most of you figure out that really you just need to know what are these variables and how to apply them in the equations. That there's not really a whole lot of higher level stuff, that you just need to know what are the variables and then how to apply them in these equations. Now that's not easy, of course, but with practice you can get that. All right, so the kinematics, which as I said will be paired with things from Chapter 8. In Chapter 8 we have several different things. We have energy and work. We have Newton's second law, and you're going to see all of this in some variant, in some form. And then we also have the conservation of angular momentum. We've worked problems from all of these, and you have some from all of these types in your homework. And I would certainly look at your homework because, sometimes your homework is a good place to practice for the test, but sometimes I'll just go in your homework and I'll say, oh, this is a good question. Let's just pull this and we'll use it in the test. And I'll change the numbers and I might change it around a little bit, but it's largely the same. So I would certainly use the homework as a study guide too, as well as the old exams. Newton's second law, do this first. You'll need to know how to find the net torque on an object. Remember, that's where we have the clockwise, counterclockwise torques, and we have to add them up, remembering that our torque is equal to RF sine theta. By the way, there is just a cross product that you'll need to do. We'll do one, or I'll show you one in just a minute. But you'll need to do a cross product. It's a separate problem. I give you R, I give you F. You have to do the cross product. So make sure that you can do that. I think it's just worth 5 points. But I just want to make sure that you know how to do a cross product. So you need to find the net torque. Remember, our clockwise are negative, counterclockwise are positive. You need to be able to find the moment of inertia. Sometimes the total moment of inertia is the sum of one or more parts. So, for example, if I have, I don't know, like in the Richard Pryor bit from the toy, where you had the hoop and then you had the cylinder, to find the total moments of inertia, you added them up. Or sometimes we've worked problems like where we have, I don't know, like the merry-go-round and the kid jumped on the edge. That was doing the cylinder and then treating the kid as a particle. I think in the homework you had one where you had a disc and you throw a lump of clay onto it, something similar to that, where you have to find the total moments of inertia by adding up multiple parts. You'll have to do that at least twice, I think, once or twice on the exam. Make sure that you're up to that, and if you have questions about that, we can look at it before we leave. Then Newton's second law is that torque equals I alpha. So once you know the torque and once you know I, you can find the angular acceleration. And then from this place, you'll go into a kinematics problem. Once you find the acceleration, then I can ask you a variety of things like, what is the angular velocity after a certain amount of time? What is the angular displacement that it travels through in a certain amount of time? There is no quadratic formula. I don't think there's any substitution as far as this. There are some where you're solving by substitution in some of the other problems, though. So where you take one equation and plug it into another. I've tried to make it so that it doesn't get complicated. I have made it so that the substitution doesn't get complicated, but just be aware of that. Okay? So that's our Newton's laws. Sometimes also we'll have this go into our energy and work. Remember, we had a couple things that were relevant here. The kinetic energy is 1/2 I omega squared. So it might be something as simple as what is the kinetic energy after a certain amount of time? You find the speed. After finding the acceleration, you find the speed, and then you can determine the kinetic energy. Also remember that our work energy theorem applies here, that work causes a change in kinetic energy. And remember that our work, remember before it was force times displacement, and our rotational scheme is going to be torque times theta. So if you know the angular displacement and you know the torque, then you can figure out the work that's been done, which is also going to be the kinetic energy. All right, so you can approach work energy problems from that direction too. All these equations, everything that I've listed here is on your equation sheet. All right. Now finally, angular momentum. First of all, angular momentum is equal to I times omega. Remember before, linear momentum P was equal to m times v. So this is the same, or not the same, but as we translate into our rotational view, this is our inertia, this is our velocity. So largely the same as what we were doing before. Excuse me. And we need to recognize that Li is equal to Lf. That are in a system with two or more bodies, the initial angular momentum remains constant. Now, it might shift around from one body to another, and so we did several problems where we have objects that change their moments of inertia. So like, for example, in your homework, there's a problem where you have those four balls that are rotating around, and then the balls all move in. It's sort of like the figure skater that brings her arms in, and that causes the rotation rate to change. I initial, omega initial equals I final, omega final. So like in that homework problem with the four balls that are spinning around, when I pull my arms in or cause the masses to come in, that decreases IF, which causes omega to increase. So sometimes we're only dealing with one body in angular momentum problems. Sometimes we're dealing with two bodies. Like, for example, if you look back at some of the old tests, I think we worked one like this in class, where I have two objects, say a disk and a bar that are both spinning, say this one's spinning in this direction, this one's spinning in this direction. They each have their own angular momentum, and then we take them and we put them together, and we want to know what is the final angular speed. So in this case, I have an angular momentum here, I omega plus I omega. I'll call this 1, 1, 2, 2, and then that is equal to I1 plus I2 times omega final. This is just like our perfectly inelastic collisions that we saw in chapter 5, I think it was, with momentum, where remember I had two blocks that come and they stick together and they move off at the the same speed. Same thing is going on here. I have an angular momentum here, inertia and speed, and then they stick together, or you engage them in some way through gears or however it is that you want to engage them. They have a combined moment of inertia and then a final angular speed. And that angular speed might be faster, it might be slower. In this case, the angular speed would depend upon the moment of inertia of the different bodies. Like if this one had a bigger moment of inertia and a bigger speed, then the final speed would be clockwise like this. Be careful with this that you get the omegas in the right direction. Counterclockwise is positive, clockwise is negative. All right, let's see, I think that's it. You're not going to have to do any derivations for moments of inertia. That's it for chapter 7 and 8. Chapter 9 is fully take-home, so you won't see that at all. Even the stability and stuff, you're not going to see that on the multiple choice. Nothing from chapter 9 on the test. Though, of course, you'll have to turn in your take-home, and it is worth 30 points. It's not insignificant. 30% of your exam, though the exam is normal length. I take that back. It's 10 multiple choice questions, so that's a little bit shorter, and then 5 free response questions. One of those is just a cross product, so hopefully you can get that out quickly, and the others are more complicated. Okay? So you have 5 free response. They're just not worth as much. They're worth on the order of anywhere between 5 and 15 points. You have a couple 10-point questions in there. Remember, with the cross product is R cross F. Let's say I have 3I plus 2J, and crossing that with 4J plus 2K. All right, you have to do FOIL, where I do first, outer, inner, last, realizing that the J cross J terms go to 0, and then you have to figure out what is I cross K, what is J cross K, and what is I cross K, J cross K. Anyway, there are three terms. I'm missing one right now. But you need to know what are those three terms. Um, I realized the other day, you can use your right-hand rule, and we're going to use the right-hand rule next semester quite a bit, where you won't be able to just memorize it. But if you want to just sort of not worry about the right-hand rule for this test, that's okay. You can remember our three combinations, I, J, K, because they're always going to be in order. Let me show you what I mean. I cross J is equal to K. Um, K cross I is equal to J. And then hold on, let me see. And then I have J and K. J cross K is equal to I. So notice these are all in I, J, K order. Sort of bear with me. See, I have I, J, K as I move left to right. And then notice here I have I, J, K as I move left to right and then loop around. And here I have I, J, K. And then, of course, you know, I think you know, that if I switch any of these, like, for example, if I do J cross I, that's what? Negative K. So if I switch a cross product, it negates the answer. Or you can use your right-hand rule to remember these, but you need to remember these in order to do your cross product, okay? You won't get full credit on that if you don't get them correctly. Okay? All right. Then finally is the thing on mirrors. I think I gave you two questions, one of which is more straightforward. I give you, say, the object distance and the focal length, and you tell me what is the magnification. So in that case, you would solve for the image distance, and then you would tell me the magnification. Remember, we're dealing with these two equations, 1 over f equals 1 over q plus 1 over p. And as I said, I have you one problem where I give you the focal length, or I give it to you. I give you, say, the object distance, and I ask you what is the magnification. That should be fairly straightforward, but you need to make sure that you understand that I'm never going to give you the sign of the focal length. So remember with mirrors that concave mirrors, which are like this, have a positive focal length. Convex mirrors, which are like this, have a negative focal length. Convex mirror is like a security mirror. Concave mirror is like a makeup mirror, or like the big mirror where you look either upside down or you look or upright. So you'll have one like that. Then you'll have another, which you have some like this in your homework, where you don't have, I just say I give you the magnification and I give you Q or P. I don't give you all the information that you can do, so you have to substitute one equation into another. So practice that in the homework. There are some questions like this in the homework and on the old exams where you have to substitute one equation into another. All right, so the second one requires substitution. All right, so those are the two types of problems that you'll have. They'll only be mirrors. They'll only be spherical mirrors, either concave or convex. I might not tell you what kind of mirror it is, but you can identify the mirror based on the type of image that it produces. So it will be useful for you to at least be familiar with your ray diagrams, or at least be familiar with the types of images that the mirrors produce. Let me just summarize those. So the types of images that the mirrors produce, concave first. If I'm outside the focal point, this is my object. Hey, Sadie. My object is outside the focal point. I produce an image that looks like this. There's my object. There's my image. The image is real, and the image is inverted. So, for example, if I have an inverted image, I know it has to be a concave mirror, and I know it has to be outside the focal point. The other type is if I'm inside the focal point, and then my image is bigger. So there's my object, there's my image. This is an upright. This is a virtual because it's on the back side of the mirror, and it's bigger. This is the only scenario where I create a bigger image. This is like that concave mirror when you hold it up close to your face and you look real big. It's like a makeup mirror or a shaving mirror. And then the third Remember, with the concave mirror, if you're at the focal point, there's no image. But we won't see that. But, it's where your image goes fuzzy. The third situation is with a convex mirror. Here's my object. Here's my image. It doesn't really matter where the focal point is, but the focal point is behind the mirror. And remember, for the convex mirror, is the focal point positive or negative? It's negative, right? Anytime I have a value that's on the back side of the mirror, it's going to be negative because that's so-called virtual space. And anything that's in virtual space, whether it's the focal point, the image, the focal point, or the image distance, is going to be negative. So, for example, this image distance for this image will be negative. I'm never going to give you signs, however, for these problems. I'll describe the image and I'll describe the mirror. Sometimes I may or may not tell you what type of mirror it is, but I'll tell you what type of image it forms, and then you'll have to figure out that. So, for example, if I told you that a mirror produces an upright, smaller image, you would know that it has to be a convex mirror. Hey, John. Right? You would know that. If I told you that it's an upright, bigger image, it'd have to be a what type of mirror? An upright bigger be a concave mirror, and then further that image has to be virtual. So know these three types of images that are formed by mirrors, um, and you can use your ray diagrams for that. So let me just sort of summarize here. So this is an upright, virtual, smaller image. And that's like our security mirrors. Two questions on that. And then also there is a multiple choice question, several multiple choice questions, sort of probing your knowledge about do you know what types of mirrors produce what type of images, what these mirrors do and how they respond. Look back in your notes on mirrors. And then there is one question where I give you a mirror with several rays and I ask you which is correct or incorrect. All right, so you need to know those basic rules for drawing the rays. Remember, for those, let's do the concave because it's easiest. In fact, it's a concave mirror. All right, one of the concave. Remember, my rays look like this. I go parallel to the axis through the focal point. This is the focal point. I go through the focal point parallel to the axis. I go to the center of mirror like that. And I go through the center of curvature. Oh, shoot, I should have drawn it back. This is more complicated. Well, I go through the center of curvature, and then it goes back upon itself. Sorry, I should have drawn the image, the object further away. Look back at those and make sure that you know how to draw the rays for the concave mirror. It's this scenario, actually, okay? So make sure you know how those rays look, okay? Any questions so far? All right, how y'all feeling? It's not an easy exam. Like Chapter 8 is a tough chapter. All right, I don't want to scare you, but I want to, scare you a little bit. Chapter 8 is historically just a tough chapter for students. But these are the types of questions that you'll need to be able to answer. Any questions, John? Any areas that you need a little extra oomph in? There won't be any derivations of moments of inertia, right? Like you did on the take-home. But you do need to know how to find the moments of inertia for a system of particles. That's where you say the sum is mr squared, the sum of mr squared. Or you need to be able to find the moments of inertia of a rigid body, like a hoop, a cylinder, a sphere. You don't need to be able to derive them. You did that on your take-home, and I think most of you have gotten that. The ones that I've seen have done it correctly. But you do need to know how to calculate it. I'll give you that table. It's largely you look at the table, figure out which object am I talking about, and know what is the mass and what is the radius. Good question. How y'all coming on your take home? I made good progress on it? Made some progress? I was going to cut short this morning unless we have lots of questions and let y'all sort of mingle on your own because I know a lot of you don't know one another. But I do encourage you to work together on the take-home, not copy your take-home. I mean, it's your work and you want to honor it. But you can work together and maybe compare answers or whatever if you wish to do that. If you don't wish to do that, that's fine. Then you can just go your way. Um, but in a few minutes, I'll let y'all do that. But first, we have some time. Do you want to work through any types of problems? The angular momentum, the Newton's second law, the kinematics, the optics. Sure. Yeah. Let's look back at some of the old exams. They're a good place for you to practice. And see, this is a slightly older. I don't think we worked this in class. Oh, let me also tell you that there are no centripetal force problems. We worked some centripetal force problems in class, and I told you to be prepared for that, but I decided not to put it on the test. Like, it wasn't a big part of that chapter. You remember, like, the car going over the hill and stuff like that? You're not going to see that sort of thing. All right, so here I have a hoop that can rotate. This is fall 14. Can rotate about a central point. Actually, no, let's not do this one. Let's go to another one. This one's in the back of your book. Did we do this one? Right, tell me. Problem number 11. Eli, we do this? Okay, let's take a look at this. If a cylinder has a mass of 3 kilograms and a radius of 2 meters, it spins about an axis through the center, and this shows the cylinder from above. A force of 10 newtons acts right here at an angle of 30 degrees, and then I have a second force that's acting there. So I need to do a couple of things. The first one actually asked me, what is the net torque? And to find the net torque, I look at the forces. I have force 1 causes a, what's that, a clockwise torque. So it's a negative torque 1. This one causes a counterclockwise torque. So it's a positive torque 2. So the net torque will be torque 2 minus torque 1. I'm just adding them up, and torque 1 is negative because it's clockwise. And this is equal to torque 2 is 20 newtons times 2 meters. The angle between these is 90 degrees, and the sine of 90 is 1. Torque 1, you got to be careful here because my angle that I want is actually this angle, 60 degrees, is going to be, so it's going to be 10 newtons, 2 meters, times sine of 60. So that's 40 minus sine of 60 is that a half? I always forget. Oh, it's 0.86. Look, I'm going to make this 30 just to make the math a little easier. So let's instead say that this angle is 30 degrees and this angle is 60. All right, so that's 20 sine of 30, which is 10 newton meters. So my net torque then is 30 newton meters. It's positive, so that's counterclockwise. And then I also need to find the moment of inertia, I, and then I go over to my table, and this is a disk, which is the same as a cylinder. And that moment of inertia for a cylinder from my table is 1/2 mr squared. 1/2 of 3 kilograms times the radius, which is 2 meters squared. 3 times 4 is 12, so that's 6 kilogram meters squared. So the steps are all going to be the same on these. Find my net torque, find my moment of inertia, and then the next step will be to find the angular acceleration. Alpha equals torque over I. My torque is 30 over 6. So I have 5 radians per second squared. Those steps are all going to be the same in any of these problems. There might be a slightly different approach on how you find your torques or how you find your moments of inertia, but those steps will all be the same. Find my net torque, find my moments of inertia, find my angular acceleration. And then you need to go into, well, what else is it asking me? Let's see, I've answered this one. I've answered this one. Oh, I want to know the angular speed for the cylinder after 3 seconds. So I would say that alpha, or excuse me, omega equals omega naught plus alpha t. That's 0 plus 5 times t, which is 3 seconds. So it's 15 radians per second. And it is counterclockwise because it's positive. And then what is the kinetic energy? The kinetic energy is 1/2 I omega squared. And that's going to be 1/2 of 6 times 15 squared. What's that? 675 joules, or 680 joules. Something similar to that. It might be slightly more complicated in how you approach the kinematics or the energy. And I could also ask you, what is the work being done? What is the angular displacement? Those sorts of questions. But something very similar to this, right? Yeah, Nicole? Oh, okay. Yeah, so I think on this test I had intended to put it from the other. But anytime I'm measuring a torque, let's say I have a force applied here. Say that's my force. My angle is always between the moment arm and the force. And so here my moment arm is a vector that extends from here out in this direction. And so I'm always going to give this angle right here between the force and the moment arm. All right? And here I give the vector from the tangent line. But notice this line is not the same as this line. It's 90 degrees away from it. So my moment arm, the angle theta for my torque is always between the vector F and the vector R, which is going to be along the radius. It's a radial, along the radius of the spherically symmetric thing, in this case a circle. Okay, is that clear? You shall have a problem similar to this, so make sure that you can go through. There are different variations of this. You can look back at the old tests and see those are in the homework as well. Ready, people? Any other questions? Brennan, does that help a little bit? Listen, though, I know that you can sit here and watch me do it, and that's all and good, but really, when the rubber meets the road is when you sit down with a blank sheet of paper in front of you and you try to do it. Because, as you know, as you found, that's often a lot more difficult to do. Right, so I recommend that you print out some of the old tests or print out maybe the homework again and work through it, but without any help. Just do it all on your own. And that'll really tell you how well prepared you are for the exam. Can you do this on your own without any help? Print out the old tests, the homework, get your equation sheet right next to you. I'll give it to you for the test, and then try to do it all on your own. Okie dokie? All right, well, I'm going to leave. That's okay. But again, y'all can work together, even sort of. I don't want you to copy. Like, I want you to be honest in your work, and I want it to be your work. But if you need a bump in the right direction, ask the people in the class because I'm okay with that, with y'all working together. All right? Okay. Let me wind down. If there are any last minute questions, let me know.